All right, we are live. I was sending a couple messages to some people that aren't here yet. Uh, no, it says okay. Chad's doing the quiz. We're good. Uh, and I talked to Cody last night. I don't know why. So let's see. Yeah. Let me send a message to Cody real quick. Ah, while you guys get set back up. Cody. All right. I've sent messages to everybody that's not here, which is some would say more than they deserve. Because you got your instructions, right? Alright, let's get started. Hope everybody weathered the storm okay. It was storming hard here. But it looks like it's all over. Like, so that's good for how bad of a storm it was. Alright, this first lesson is kind of just an overall overview of series circuits. I would probably argue that it's the most important lesson because it covers the most about series circuits. Alright. Finished my water last night. What value remains the same at all points in a series circuit? That would be current flow. So in a series circuit, current flows in one direct or from one point to another, and it can't go anywhere else. Let me open up Paint. I need to just put it here. Alright. Sorry about that, if that was loud. Alright. So, in a series circuit, you have your battery, and current goes. That was bad. Uh, I'm a little bit off to the side of my thing, so it's. Anyway, current goes from around the circuit. So, it leaves from the negative side of the battery, flows around, and comes back to the positive side. There's nowhere else for that current to go. So it's like a closed loop system. Uh, of like imagine if it was full of water, like a pipe that's full of water in a closed loop. The battery being the pump. There's nowhere else for that water to go. So whenever the pump pushes it, it's coming back into the pump at the same time. How many possible values do you need in order to find all the other values for a component? 2. So of your values, uh, and I'll get more into the formulas here in a minute. Where's my pointer? There we go. I wish this was a little bit bigger, the pointer here, because I'm sure y'all can't even see it. All right. Let's change the black. So in your when we talk about formulas or the values for a circuit component, we have. It always resets my pin size. R, I, E, and P. If you are going this way, you multiply the two columns to get the next column. If you're going this way, you divide the two columns to get the next column. You can skip, so you can do P divided by P divided by I to get E. So you can skip a column to get the column that you skipped. So this is resistance. R is pretty straightforward. This is current, voltage, and power. So resistance times current will give you the voltage. Current times voltage will give you power. Going back the other way, power divided by voltage will give you current. Voltage divided by current will give you resistance. If you have any two values in here, you can solve for basically everything. It might take you a couple steps to get through that. The exception to this way of doing the formulas is if you have R and P, it's not straightforward. That is where the standard way of doing things, the way that they taught while I was coming through, comes in. Let's just delete that. Let's do some lines. I should have just copy pasted. That would have saved me so much time. Alright. That looks so much better than the one I did yesterday. If you watch yesterday's video, it's just handwriting. So, the magic circles. The way they work, and I think I covered them a little bit last week. So the way they work, you cover up the value that you're looking for. You cover up the value that you're looking for, and then you do the thing that's still showing. So if you're looking for resistance, you cover up R, you've got E over I. You cover up I, you have E over R, and you cover up E, it's R times I. So back to... Oop. There we go. This is my favorite one, ERP, E squared RP, and then P I squared R. You can see these two right here are the ones that are covered by the standard way. And you can do probably 90% of the work just doing this. Well, I call it standard way. Put it on the chart. But if you have R and P, you'll have to use that to solve for one of the other values. The opposition to current flow provided by resistors can simply be added together. Yes. So, going back through this, I'm probably going to handle a couple questions here. When we have covered how you go across the rows on the charts, and you're just going to create more rows for every circuit component that you have. So this would be our total. Below it, you're going to put like R1, R2, R3, and so on and so forth. And then across from that, it's I1, I2, I3, E1, E2, E3, P1, P2, P3. And that's the different components of the different resistors. But if you are, and we've covered how to go across on this chart. If you're going up and down, resistance in series adds up. Current in series stays the same because it doesn't have anywhere else to go. Voltage in series adds up. And power in series adds up to your total. So there are all of your how you combine everything. It is not necessary to disconnect the power from the circuit before taking resistance measurements. It is necessary because you can damage the meter. Series circuits have one current path. That's like the most fundamental thing that we're going to cover. The voltage of batteries connected in series will add. So voltages add algebraically. That means, in this case, if you had a bunch of batteries, and I'm going to do more of a pictorial diagram. If you had like 3 batteries, and they were connected, in a circuit, ignore that there's not a resistor here. So they're connected negative, positive, negative, positive, positive. So they're connected in a circuit, currents flowing, and they're all 1.5. They're all AA batteries. They're all connected. The total voltage in this circuit is going to be 4.5 volts. Now, if you swapped one of those around, or put a new battery in that was backwards, so this battery is flowing against the grain, and let's say it's 2 volts, and it's flowing backwards. So now your actual voltage isn't 4.5, it's going to be 2.5 because it subtracts. Larger resistors drop more resistance, or more voltage. Larger resistors drop more voltage because they provide more opposition to the flow of current. Voltage is the difference of potential. That is the definition of voltage. Software unknown value of person must know 3 of the 4. No, just 2. Yes, there's several different ways to get a value in this. So you can solve it using the other values in the row, or you can solve it using the other values in the column. And I know this has gotten a little bit cluttered, but if you were looking for a resistance and you had literally all the other values in the circuit, oh, excuse me, I'm sorry. All right. If you have all the other all the other values, and you're looking for resistance total, you could do E divided by I to get R, or you could add your resistors up to get the total. What this question is suggesting is that you do both and make sure you get the same number. And that's the same question again. Let's check the results. Cody came in, Covies talked to me. Jeremy had done it already earlier. Just those two. Okay. I don't like shuffling the questions right now. Alright, so instant feedback. New quiz is up. I'm only running 5 minutes behind. Yes, Jeremy, I just put the second quiz up. And I might need to move the live stream up so that we can not run into the run past when it's supposed to be over. Not doing it this week though. All right, guys. I will talk to you guys in the next one. I'll see you at 10:45. Yeah, 10:45.